This lecture is entitled VolterraFilters, but we're going to start out going to a little bit of depth on a common adaptive filter problem to motivate the Volterra filters. So this is echo cancellation. Echo cancellation is used in nearly every communication device. And the idea is that sound comes from the far end, that's the person to whom you're speaking on the phone, goes out the speaker, and that could be the small speaker by the ear, it could be your Bluetooth device, whatever it might be. Some of that sound will come back into the microphone. In the case of speakerphone type operation, much of that sound will re-enter through the microphone. And in the case of a regular phone operation, it will be less sound, but it's still noticeable. So if you follow this upper chain, this is the sound coming from the far end, going into the room, and bouncing back into the microphone. In addition, of course, this is you speaking on your speakerphone, and you want to be heard. And your voice may actually be quieter than what is entering into the microphone from the speaker. Now, if nothing is done, the far end speaker is going to hear himself, and you've all heard that from time to time. That's the echo that sometimes people hear, especially when you have a bad connection. And every once in a while, it shows up for a moment and then goes away, but sometimes you may even have to drop the call and try again. So what is going on? How do we get rid of this echo? This is done in devices of all sorts. And the straightforward way to do this is to take the speech on its way out to the microphone, run it through an adaptive filter, and predict what it will see coming in through the microphone and subtract it off, so that what we're left with is just the local speech and not the echo. Usually this is done with an NLMS adaptive filter, although I have seen it done with affine projection filters to get a little bit faster convergence. And there are some variations on this basic structure, but a key component is this new part, and this is the double talk detector. We have this problem where we need this echo canceller to adapt very quickly in case of changing acoustic situations in a room. However, if it adapts very quickly and there is a significant amount of noise on the desired signal line, which would be this one, then the filter may get some significant misadjustment error. And any misadjustment error is going to cause a problem. We would really like the echo to be 30 to 40 dB below the speech level. So misadjustment error is a big problem. And of course, the faster your adaptation, the more misadjustment error you're likely to have. So we want to stop adapting when the person at the near end, that's you, is speaking. And that's the job of the double talk detector. So it will be monitoring the far end signal and the near end signal and determining when there is speech occurring at the near end, and at that point it will turn off adaptation of your adaptive filter. When the speech goes away, it turns it back on. It may even be a little bit smarter than that. It may simply turn the beta way down when there's near end speech. When there's only far-end speech, it may turn it way up. And when there is no far-end speech, it may turn off the adaptive filter as well to keep it from adapting on spurious things. So having this adapt at the right time is a critical part of the adaptive filter. So recording what I just said for posterity. One thing to note is there are many papers on double talk detectors, and it's really one of the key ingredients of an echo cancellation system. So, as I said, much work has been done on echo cancellation systems, double talk detectors, adaptation schemes, and so forth. For example, in a room, we may have a very relatively long echo. Sound travels at about 1 millisecond per foot, and if you're sampled at 16 kilohertz, that means 16 samples per millisecond. So if you have walls that are 8 or 10 feet away, let's say 10 to make the math easy, that's 20 feet of travel times 16 is 320 taps. So your filter is already starting to get longer, which of course slows down the adaptation. We can do frequency domain adaptation. There are various other schemes that can come into play, but regardless of how it's done, echo cancellation is a bit of a trick. But people worked on this problem for a very long time and found that there's another limiting factor. You won't see it if you simulate this in MATLAB, but you see it in real life. That is this box that was unlabeled before. This would be the amplifier, and it has nonlinearities. The speaker itself will have nonlinearities as well. Well, we can't cancel a nonlinear operation with a linear one. So we need to do something about this. There are also many ways of configuring the system to deal with this, but let's talk about how we do an NLMS adaptive filter with nonlinearities. Recall that in a system such as this, when we talk about linearity, we're not just talking about something that forms a straight line in some plane. It has to be linear in terms of you double the input, you get a doubled output. So an example of something that's not linear is this. But another example of something that's not linear would be this. The tanh function is going to give us a nonlinear function that's actually pretty common, or closely approximates what happens in some circuits. They don't immediately clip, but as you get near the range of the output, they start to saturate, and you get this hyperbolic tangent-like behavior. For now, we're going to consider or assume that any nonlinear function of interest is going to be continuously differentiable. That would make sense in something like this type of a system where we have an amplifier that is hopefully as linear as possible. And since it's physical, we can't have sharp discontinuities. So this is a reasonable assumption. This allows us to approximate it with a Taylor series. And as we've seen before in this class, we could now approximate or calculate our result based on something like this. Here, each of these additional x terms is going to be the Taylor series terms that you get, the x squared and the x cubed. We don't actually need to put in the Taylor series weights, which would have the derivative evaluated at a point divided by n factorial types of things. We don't need that because the weights are going to adjust to whatever it is, and so we can assume that any scaling would be absorbed by our adaptive weights W2 and W3. We may also have a lot of cross terms. Depends on the function. If it's a memoryless function, then things might get easy and we get rid of the n-1 terms, but we'll still have cross terms. Such as x n x n-1, x n x n-2, and so on and so forth. Because of this, the actual number of terms that we may have can be huge. Just a moment ago we talked about an echo canceller that maybe has 320 coefficients, and in practice it may actually have double that to account for secondary echoes. Well, if each one of those 32 coefficients is now we have the x squared and the x cubed terms, we've taken 320 and it's now almost 1,000 coefficients length filter. If we add in the cross terms, it leads to an explosion of terms that becomes impractical. So let's see what this looks like then with the second order filter. This first part is just a regular filter. That's the inner product of W with X. And I've added the superscript 1 to show that this is the first set of weights associated with the regular linear filter. Next, we will have another set of weights associated with the cross terms. If we have all the cross terms, this becomes a double sum. X n minus k 1 and x n minus k 2. So in this case we have p squared plus p, or p plus 1 squared plus p plus 1 total terms in our filter, and you can see it exploded quite quickly. If we were to go to a third order filter, that would be even more significant. So for example, we could have y1 or yn is equal to w1 0 x of n plus w1 of 1 x n minus 1. Let's just keep p equal to 1 at this point, plus, and then we have w2 I forgot to put this in there, k1 k2. Okay, so W2 0, 0, x squared of n plus W2 0, 1, xn x n minus 1 plus W2 1, 1 x squared n minus 1. Okay, so I expected one more term, but this is actually the same as the 1, 0 term because of the commutativity of multiplication. So it's not quite as bad as I made out. It still is a lot worse than 2 by 2. So we can define our W1 matrix like this and our W2 like that. Or our X matrix and our W matrix as shown here. In this case, X2 is going to include x squared of n, x n, x n minus 1, and x squared of n minus 1. And W2 will be the corresponding coefficients as you see there. Well, now if we find our autocorrelation matrix, we are going to get several of them. Like this, where R2, R3, and R4 represent the second order, third order, and fourth order statistics of x of n. This is a problem because, in general, our x may be poorly conditioned. The R4 versus the R2 matrices may have vastly different sizes and problems, so that's going to slow adaptation. So it seems like all I've done so far is talk about all the problems with the Volterra filter. Well, there are ways around many of these problems. The first thing is, we've already mentioned, keep the nonlinear order low. 2, keep the filter short. Well, maybe circumstances won't allow us to do that, but we'll talk about ways around this. And very importantly, remove or prune, if you will, the higher order terms that are not needed. So if we go back to our motivating example, it's very likely that the nonlinearities are zeroth order nonlinearities. In other words, we have this large echo, but the echo is a function of the room, and the nonlinearities are a function of the instantaneous level of the amplifier. So it may be, in such a case as this, that we can find a way to reduce the length of the Volterra filter. Just getting rid of all the delayed nonlinear terms isn't going to help directly, because those nonlinear terms have gone through a linear convolution, so they're spread all over the place. But we'll come up with an architecture right now, which is this. There are several variations, so I'm just going to put this up as an example, and that is that we come in with our desired, or with our signal to be filtered, and we go through a linear filter, and we have some target, adapt, and we try to get that down to 0. And then let's put this in a different color just for kicks. We'll pull this off and go into a second filter. This filter will be our Volterra filter, our nonlinear filter. And so we're actually going to add in one little step here, a transformation step. And in this one, we calculate maybe our x squared of n, x cubed of n, x fourth of n, and really we should also include x of n in this, so let's fix that. We're going to do that right in there, and so this will be a high order memoryless filter. It could also be not quite memoryless. It could have, say, maybe 1 or 2 samples. And this lower filter then takes care of the nonlinearity, removes and this upper one removes, for example, echo room response. Finally, we take our output right there. Actually, it depends on our application. I guess for the echo, we would take our output right over here. So this type of an arrangement can make a Volterra filter work well. It may also be that you're just trying to do some system identification, and you really don't care how fast it adapts. You don't care how much processing power it takes. Then you can use a very large Volterra filter and just run the thing for a very long time. But remember, you shouldn't go too high of order if you're going to do that, because the your R matrix, your covariance matrix, may have poor conditioning, and you may get some results but that aren't as good as you'd hoped.